these results, I can show you exactly the same results, so we're not taking it here. So the error of this approximation in this specific benchmark is just, so that when we say error, we mean the elapsed time that the internal run of mgrid told us. And the full sampling, the full timing with feedback took 2.09 seconds. This one took 2.15, which is approximately less than 4%, 3 point something percent. Every time that you see, instead of putting all the values, since we only sample at specific points in time, as you can see here, first we sample at 6.725, 1875, 15 milliseconds. Every time one of those, we assume that that lives for a long time. If you see so sampling is tricky. If you try to mimic with your sampling exactly the image that you have behind, you're never going to be perfect, especially in thread environments. What you want is that you want the errors to compensate. So if you determine that a particular thread should have taken a little bit more at 1 IPC, if you say this should go at 2 IPC and it should have been 1.8, and you capture the exact amount of time, then you want to have a lesser IPC prediction later, so that your final time is good. And this particular example we just had was good enough. But you also want to make all the samples give you representative values of the metrics that you're interested in. So if all those samples, the instruction streams that you get are representative, it doesn't really matter if you get exactly the same points. And the other thing is that if you're comparing one image to another one, you have to always take into account that those images may be shifted because the time doesn't fall exactly the same because you're not 100% precise locally. You should be globally more or less precise under an error, but locally you're not 100% precise. So, for example, you notice that the spike in yellow before the spike of application, that's when the sampler decided application should be started, because it didn't really track the loading of the application correctly. And then the application, more or less it tracked it correctly, but in certain points it didn't. By the way, this is only one CPU. The other CPU we didn't put it so that it didn't mess up. So it captures certain moments in which the application goes down, and those moments are like very small peaks, like the real application does. And it captures the moments that goes up better. And you should see that the yellow line is an average of all the small peaks that you get in the other side. Of course, depending, we hacked this up, so if you really want to be more precise, you could have a bigger application and you shouldn't be putting 5 million instructions to function, or you should change those numbers or have something better. But here the main problem is that the loading of the application is very intrusive for a very small application. So we didn't get that right on the way. So this application is finished, so if you go to the output, okay. And if you grab the lapse in the output files, these are the 3 output files that we have. The dynamic sampling says that you got 2.15 elapsed. Since it's a 2-thread, you shouldn't be looking at the 3.59 because that's adding the 2 cores up. And the other one, the full timing, said it got 2.09. So we're frankly very, very good. I'm saying this is just an example. The full timing, even though it's good because it's only approximately from 192 elapsed to 2.09, it's an 8% error. As you saw from the images are totally different. If you run that application longer, that's 100% developed, because you basically don't know what the application is waiting for the out thread, and that's a very important part. And here you can also plot here all these values. Okay. The main difference between this and that is that here we plot in both CPUs, and that I haven't changed this script to plot it using boxes. It plots them using lines, so it should be, since we're sampling, we should plot it horizontally. But it works very well if you plot the full timing, which is right, I have it there. Okay. So if you plot the full timing, up here the numbers that we had before. Okay, so I'm going to go to the last experiment. Okay, I'm going to kill it because those are lots of samples. There's one last experiment which we wanted to show you, which is really nothing that we would like you to do, because we believe in sampling as the good thing. But many people, and we have used it, it's a very good tool for debugging or for knowing what happens. So some people, they tell you, oh, we have an operating system, you run the full stack, you run everything. They say, yeah, but I only want to know, I only want to have a trace of my application. I want to have your infrastructure, but I want a trace of my application. So we modified COTSon and SimNow to track stuff. So we use the same tricks that they use to bring stuff in and out, which is basically the XGet and the XPut. They use a fake instruction, which is CPU ID with a fake number, and so they capture it, and they let us into that hook. So basically what you do is you can go into any application and you can say, I want to begin the trace here, I want to end the trace here. So you will only receive the instructions that were from that point to that point. Or you can also say, I want to begin, we also have scripts that do that, so we also have pre-compiled applications. I only want to trace from this benchmark, I only want to trace that benchmark. And you will get that coupled with the CR3 tracing, which is the one that traces what application is running, allows you to determine, I only want to get the trace for this application, or I only want to get a trace for this view. It lets you do a lot of stuff. So, okay, and another good thing that has this application is that we talked about a lot about Lua applications, blah, 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 the concatenation of Lua files. This one is really, has a particular value which is called iterations, which is within there. So basically what we're saying is that this file is going to get the value iterations, which is not in this file. And basically what we are doing here is we are putting all the selective tracing. I think we are using the dump. Yeah, we're using the dump. And we dump it to a file which is called selective tracing.this.number of iterations. So we're going to run this code that we see here. It's inside the SDK, but it's a very stupid application which basically says the trace is beginning and runs a loop for the amount of iterations that we want, and multiplies, creates a value, and prints the value out. It's very stupid. We're going to run it with 3 inputs. Basically what we're going to do in this application is we're going to get this benchmark that we've compiled, we're going to put it inside, we're going to run it with 1, 2, and 101, and we're going to see the output. So we say bin run selective tracing, and then we're going to send a 1. Okay, so this one waits a lot because it's copying the file input, it's doing all the stuff. All this time, it's basically waiting. Well, in the middle of all that time, it's yes, we could print out a we're starting tracing now, we're starting ending tracing now, that's what happens. So this is probably 5 seconds. Let's execute this with 2 and let's see the output.